The live stream yet. Hmm. This is mildly concerning. Awesome. I can hear myself, which is a good sign. I was terrified. Cool. If those words didn't go through, thank you so much everyone for joining. This is the first live stream of the year, so happy New Year. I'm excited to kick off the series again. Excited to learn more from top Kaggle solutions. If you're new here, or if you've been watching, I'll just do a very quick recap. So give me 30 seconds. But if you're new here, I try to live stream top solutions from different Kaggle competitions. Today being the Novozymes Enzyme Stability Prediction one, and the goal is to like understand or have a good high level overview of the approaches used by top teams. Usually in the first half I spend some time understanding the problem statement and like showcasing relevant discussions, and towards the later half we condense and understand the top solutions. So that's what we're doing today. Thanks for joining. As a reminder, I am also live streaming a few more things every week. So if you are interested, I am also live streaming a study group about the deep learning book. You're welcome to check that out. And to make me more accountable, please consider watching this video and sharing your goals with me. So I've shared all of my goals for 2023 in this video. It's on the top on the channel. So if you have the time, consider watching it, or don't. There are better things to do with your time. Anyways, that's it for announcements. So for today, as I said, we'll be understanding this competition and then stop solutions. So the goal here was to predict enzyme stability with different temperatures. And in the text, the organizers explain how enzymes are relevant in different things, how they help in detergents, in creating bread, wine, beer, all different important things. And with temperature, or as temperature rises, enzymes become unstable. So the goal is to predict how stable will enzymes be with temperature. I want to mention one quick thing before we get started. There was some controversy or discussion around the fact that there was a very heavy shakeup in this competition. I still think it's worth it to learn from many of the top finishers, so that's why I'm doing it. And I'll point out a few discussions around that. So I'll come back to what enzymes are and how they're relevant, and we'll read that again. Uh, but let me get started by sharing a few more things. So I respect CPMP a lot, and I'm sure everyone in the Kaggle world knows him. Uh, at the end of his write-up, he said, despite the huge shakeup, I see that some teams were relevantly stable. And at the end, he says, after reading some write-ups, this competition was not a lottery. Overfitting was a danger, but some teams found ways around it. Um, I'll also mention some other notebooks, but before that, I want to highlight something. So let me go to Chris's profile, and I was looking at his profile. Look, in my defense, this is a better thing to do than looking up profiles on Instagram. All right, any offense is intended, but I was looking at Chris's profile, and I saw that he had done a lot, like insane amount of submissions in the last few days recently. Because I was just trying to figure out in which competition is he competing. I was competing in the auto one, and I saw him there, so I was looking at his profile. And he also shares the reason why I point this out. He was first on the public LB in this competition, and then later shook down to a much lower position. But just wanted to point out that that's the difference between absolute legends and people like me. I would have deleted my Ubuntu partition that day, but he, I'm sure, figured out why he faced the shakeup, and I'm sure he figured out all his techniques and what was the sauce to getting to the top. So, wanted to throw that out there. We'll also cover his solution, but that's the difference between uh, Kaggle legends and Kaggle looms like me. I literally deleted my Ubuntu partition when I faced a shakeup in the malware competition. Anyways, now let's start learning about enzymes and what they are. So I'm using this notebook by Moth, and I know he or she writes absolutely awesome kernels. So that's why I'm using this one. The goal of this competition is to predict thermal stability of enzyme variants. The experimentally measured thermal stability, melting temperature, includes natural sequences as well as engineered sequences with single or multiple mutations. So, what does mutation mean? The way to write enzyme is by using amino acids. And when you mention mutation, you just change a sequence in the. Let me go back. So, when you write an enzyme's name, it's literally different characters combined together that represent amino acids. So sometimes you change them, you change the amino acid or one amino acid there, and that is mutation, to my understanding. Happy Sunday to you too, Samuel. Thanks for joining. So, what is an enzyme? Enzymes are proteins that act as biocatalyst by accelerating chemical reactions. An enzyme is therefore a molecule that increases the speed of biochemical reaction in an organism. This is how they work. So the substrate sticks to the enzyme, and then the byproducts are formed. One thing to note here is the enzyme itself remains unchanged. Why is this info relevant to the competition? It's not. It's just good to know what enzymes are. uh, the info about enzyme remaining unchanged. Proteins are large biomolecules and macromolecules that comprise of one or more long chains of amino acid residues, and that's why they are known as polypeptides. Peptide is, I think, amino acid. Oh, that's mentioned in the next sentence. Peptides are short chains of amino acids linked by peptide bonds. That's why proteins are polypeptides, and this is how they are represented. So they tend to fold into each other, and this is where something known as delta delta G will come into the picture later. So Kaggle have written it as DDLG, which just shares the difference in energy when the protein is folded versus unfolded. So that is delta delta G. I'll remind you all once that comes up, but just setting up the stage here. Amino acids are organic compounds that contain both amino and carboxylic acid functional groups. If you don't know these words, or if you didn't have a painful school experience where you had to literally remember all of these, like me, I'm just complaining here. But if you don't understand these words, it's just a chemical compound. That's the most simple representation I can point you all to. But as you can see, these are different random letters, which I don't understand what they mean. But if you start looking them up, all of these have some properties, some representation. And these letters represent these amino acids. So that's where the competition starts to come into the picture. Here you can see the protein sequence, and this is the first one is the train data frame. So as you can see, this I'm sure is different amino acids combined together. I'm not going to try and point out which one is which, but this is what that represents. And after that, you can see the pH and melting temperature inside the training data. And inside the test data, you have the sequence, the data source, and then I assume you have to predict the melting temperature or something similar to that. I don't think there are other things that I wanted to highlight from this, but that's a overview of what enzymes are and what proteins are. I'll remember to upvote all the notebooks I'm going to through, and if you find these useful, also remember to support the work of the authors. Here's one more, which also shows the enzyme catalytic cycle. I also found this explanation to be quite good, so that's why I'm explaining this. But enzymes follow this cyclic behavior where different substrates bound or get binded to the enzyme, and then a reaction happens on the enzyme's surface, after which the products then leave the site and the enzyme remains unchanged, and this process keeps repeating itself. So that's why they are a form of catalyst, and this keeps happening over and over and over again on anything at all. Tarun says hello. Thanks for joining, Tarun. We are just learning about enzymes and what they are, if you're just joining, or you can go back and watch. It's totally up to you. um let's see if there are other things. I usually leave the tabs open and then try to recall why I'd left them open. But I think that's all I wanted to highlight from here. And there's some general EDA in this notebook, which I don't think is something worth highlighting for the discussion. So I've upvoted this and I'll close the tab. Darian also writes, he shares a lot in different competitions. And I think he had done a nice EDA here. So I'll again use this notebook as well. So the thing worth pointing out is many enzymes are only marginally stable, which limits their performance under harsh applications. So instability decreases the amount of protein that can be produced by the cell. Therefore, the development of ways to predict protein stability is really important, and that's why this competition is quite important generally towards the world as well. Um, these are two different programs that Darian mentions here, and these will keep coming up throughout the top solutions. So, Foldex and Rosetta are two programs that you can download, as I understand, and use them to predict stability of proteins. You can input the sequences, and they'll give you some different values. That's a broad overview. I didn't dive too much into it. The other one is Foldex, and many other ones kept coming up. So again, the challenge is to develop a model to rank the thermal stability of enzyme variants based on experimental melting temperature data, which was obtained from Novozymes screening lab. Now, if you remember, inside the data frame I had shown, there was a column for sources. Some come from Novozyme, others come from different resources, and you were allowed to use these from different sources. So many competitors have used these external data, and Chris had shared many kernels that I think were from external data. There was one very popular kernel that didn't use the training data at all. Here he mentions the Spearman correlation coefficient, and I think this seesaw is the easiest way to understand it. So -1 says that the values strongly disagree, and +1 says the value between the two predictions or the predicted and ground truth totally agree. So that's how the coefficient is evaluated, and that's the behavior of it. In this kernel, you can read this if you want. Darian explains a few more details about what's important for the competition, what's not. You're welcome to read that if you want. And here again, he mentions that usually is the rule 7C where you can that states if you're allowed to use external data or not. It was heavily used or heavily discussed throughout the competition. Some other techniques that will come up again later, ESM, EVE, and Rosetta are other ways of predicting stability for enzymes. So those are some other words we'll see. The test set for this competition contains experimental melting temperature over 2413 single mutation variants of an enzyme, and the amino acid sequence of the wild type is this doesn't make any sense to me whatsoever, and I tried to understand it. I took my pen and paper and tried to actually convert it, but later on I finally got around to reading the top solutions. I don't think it has any relevance. So uh, you're welcome to read about amino acids if you're just studying this competition. I didn't find it particularly helpful. Although Tilly, who finished TILI, that's his Kaggle username, he is a domain expert of this. So I'm sure the knowledge is useful. I didn't find it very relevant, so to speak. Please note that most of the sequences in test data have the same length 221, or some have 220 because of amino acid deletion. He talks about pH and data source and also TM, what these column relevant mention. So TM is the target column, and since only the Spearman correlation will be used, the correct prediction of the relative order is more important than the absolute TM values. That's all I wanted to highlight in this notebook. After this, Darian shows us how to set up a baseline. But again, to summarize, we learned about what's there in the test data, how enzymes behave, what are different things present in the test data and the trained data, and the main challenge of the competition. So, Chris had shared this Hugging Face Transformer starter pack, and eventually many people got around to sharing protein language models. So we'll see PLMs throughout the competition, which means protein language models, and that's what they signify. But I assume since Chris is the first one to share share baselines, this was the one that got everyone started. It might not have been the case, so please excuse that if that wasn't true. I didn't compete in this one. um, but this was a transformer based approach. And in this baseline, he says, first we transform the trained data into a new data frame with pairs of wild type sequence and mutant sequence. Next, we create a new target of delta TM from the original TM. And lastly, we feed pairs of these into a transformer and add a regression head to predict delta TM. D represents delta in most cases, so that's why I'm saying that. The NLP model interprets protein sequences as sentences, and the model interprets amino acids as words. So that's how the transformer based approach came up. There was also a GBM based approach. Chris had also shared XGBoost based baselines, which we'll again see in a second. So this was that. And what I'll do here is I'll sort by most votes. So as you can see, here are a few more popular notebooks. This one was the most popular, which says 5,000 mutations and 200 PDB files. And let's see if I want to point something else. Um, delete that search and difference features. So I'll point out these two discussions just as a reference to understanding what else was used in this notebook. So PDB, as I understand, is a way of storing these amino acids in a database. So wherever you'll see PDB in the discussions, it's just a way of, I think it's called protein database. So that's what that signifies. It's just a way of storing this information. And in this notebook, somewhere I remember it. All right, it's here. I found it. Currently, all notebooks at that time did not use Kaggle train data at all. So many notebooks ended up, as I pointed out, using data from different sources or PDBs from different sources and then creating features on top of these. This notebook, I also believe, shares an approach around that. So as you can see, there were many different approaches. There was a transformer-based approach. This again uses XGBoost, applying XGBoost to all of these after some transformations. So these are the broad two approaches. There were also other programs that people had used. So you could feed in the competition data into Rosetta, Foldex, or other stuff that was allowed under the rules. And that would also help you understand the stability, or that would give you some more info that you could work with. So that's a nice overview of the data set. Let's now move over to other discussions. This was again something similar to that. In this notebook, Chris created different features based on another data published by someone. For each test mutation, we compute the difference between PLDDT mutation minus PLDDT wild type. So again, the idea for any competition is to use as diverse data and as diverse approaches to reach to the top of the leaderboard. That's why all of these approaches come into the picture. And now what I'll do is I'll point out some cool discussions that at least I enjoyed. So the thing worth highlighting in this competition is this has been one of those competitions where raw GPU power wasn't what made or broke the leaderboard, but rather good feature and model selection from intuition, experimentation, and seeking out domain knowledge. There was a large shakeup, as I pointed out. So, as you can see, all the top teams were up and down by at least more than 100 positions in some cases. One for this particular team, but for everyone else, it was a large shakeup. And if you start reading solutions, you'll see that it wasn't just luck for all the top finishers. The first, and I wanted to like pay my respects to the winner of this competition because he's very honestly admitted that I won this competition by accident. My submission is an ensemble of GNN and some public notebooks. It scored well in public LP, but I found out the training code had a fatal bug and they ended up winning the competition. So that was a very honest share by them. Now let's see what they actually did. So let's start by reading their solution. And I'll come to Chris's solution after this post. Once I can find the winning solution. All right, found it. Sorry about that. Usually I have the tabs open. Today I must have messed up. So this is the first place solution, and this is an overview of what was going on. So they had fed in three different types of data sources to their main model. First was a wild type sequence, then there was a mutant sequence, and then there was a PDB file. All of these were fed to a GNN model, either through a graph or an embedding layer. After which, I'm trying to tilt my head and read this, but these were eventually concatenated, and MLPs are used to predict either the delta G, which tells you the energy difference between a folded and unfolded enzyme, or the delta TM. Uh, DTM was what was relevant for this competition, by the way. So let's read through this and try to understand this. The three-dimensional structure of a protein can be represented as a graph, and Shujin, who had finished sixth, had used one notebook that we look at, or one approach that we looked at. But you can imagine proteins to be something like this. Now, like I'm not going to go into exact details if this is exactly right or not, but they're something like this. They're rotating in the 3D space. This could be an enzyme. This could be an amino acid. It could be a protein. All of these three are similar, but it's basically different. All of these molecules combined together, and that's when they can fold onto each other or unfold. But because they literally are such 3D molecules, they can be represented as a graph. Nodes. So in a graph, you have a node, you have different nodes and different connections between the nodes. So nodes for this graph would represent residues. And if two residues are closer than a certain distance, the nodes are connected by edges. And this graph data was created from the PDB files linked here. The features of each node are the embedding vectors of the wild type sequence and mutant sequence generated by this particular model. And he had used Chris's notebook where he had shown everyone how to fine tune BERT and how to use those embeddings. This notebook demonstrated how to fine tune an NLP transformer for this particular competition, and it had used some external data set. So he had in this notebook used prot underscore Bert, but then Ekplank went ahead and tried other models. So this is one example of where if you use a public kernel and actually mess things or like tweak different minute things, you can actually find them very useful. So you should, my stance is always you should look at public notebooks. I at least am not good enough to be able to start from scratch, so I do it anyways. But it's usually a good idea to do that. So here's an overview of the GNN module. And the primary GNN is a three-layer graph isomorphism network. The intermediate features are concatenated, and the global readout and features of the node where mutation occurred are input to the MLP to obtain predictions. So the outputs from this get concatenated and are then fed into an MLP model. Uh, he shares the best scores for different GNN models and some more details of the first place submission. There were two bugs he highlights in this model. The GNN model output almost identical predictions for all samples in mini batch. And the other one is GNN model take wild type feature and mutant feature as input, but two wild type features were input when predicting on test data. So there could have been a case of leakage, as I understand from here. So the first place winning solution was an ensemble of the GNN with bugs and some public notebooks. I had mentioned Rosetta, and this is again different notebooks that are coming into the picture. Thermonet was an approach shared. PLDDT was also an approach shared. So again, that's why I wanted to highlight those earlier. But he shares the weights and how these were combined here. I'm skipping graph centrality because that wasn't quite relevant. Um, Tilly had shared some extra insights here, so it might be worth reading through the comments. But that's it for the winning solution of this competition. Again, a very honest write up in the sense that they admitted that uh, the winner themselves was surprised and he didn't select the right submission. He didn't expect to win, but ended up winning it. Let's read Chris's solution. And I'm not doing this out of pure fandom, but also because Chris shared that if he had used random forest instead of hill climbing. So there are, let me explain what hill climbing is. Usually on Kaggle, you have a certain submission time limit. And within that, you can ensemble as many models as you want, as long as you stay under that limit. So when you do hill climbing, in the final ensemble, you add all of your models until the score stops improving or you run out of time. So Chris had used hill climbing in his public first position, but he said if you just tweak that approach ever so slightly, you could have won in the private LB as well. That's why it's also worth covering this write up. Um, and he also says he had an unselected sub that could have won first private. The solution summary is he himself also struggled to create a local validation. Since the test data was one enzyme, he decided to use public test as validation. So the strategy was to generate as many single model features as possible, probe the LB to acquire the public test labels, and then train one model using single models as features and public test labels as targets. So he had no way of figuring out what to select for the final submission. Therefore, he used this approach. The first one was hill climbing with positive weights, and the other one was hill climbing with positive and negative weights, because these two models would not overfit and would do good on the private LB. He had also trained a random forest with sklearn default settings, but he assumed this was overfitting because RF allows for non-linearities. Uh, if he had used this, which he assumed was overfitting, he could have won the competition. I think that's a very quick overview of his solution. After this, he also shares the probing approach and what he learned, how he had used different ideas here, and the strong single model or features. You can look through these. I didn't know exactly what Rosetta Energy was or Thermonet was. Anyone who competed in this competition would know very well. But it was a combination of all of these for his hill climbing approach. And then his final submission was they had he had 27 strong features and 14 weak features, all single with LB 300 plus. So one was random forest trained with 27 strong features. The other one was random forest trained with 41 features, which would have been the first place. Hill climb with 27 strong and positive negative weights. He ended up 517, but without a bug, he would have been 227. And then hill climb, his other submission would have finished 198. He's also shared his final solution as a notebook, so you can also read through that. But again, it's really impressive to see how even the best of the best can also mess up. And this competition was really challenging in that sense that it was really hard to understand if you were overfitting or not. So that was the public first place solution. I don't think the second place solution has been shared at all. So we're reading the third place next. It has been, sorry. Um, Now, here's my side rant about this approach that Kaggle has adopted. So, I think this competition has ended, and ideally, all solutions should be listed here. But if you Kaggle search sometimes works, sometimes it doesn't. If I go to discussion and search for stuff, if I search for solution, not all would show up. If I search for SOL, some would show up, and then not all of them are linked here. So it's I don't know like how they'll fix this, but again, if Kaggle you're listening, please fix this. It's easier to find all solutions here. I can't at this moment. I don't know if maybe it'll be fixed in 2 days. Who knows? Maybe the script hasn't been run yet, the one that links everything. Who knows? Um End of rant. So now on to the second place solution. The solution is very simple. It's just an ensemble of different methods and a little smoothing at the end. So what Muhammad has done is, and I'll remember to upload this one. He used positive weights for all of these approaches, negative weights from some other approaches. Before adding them, he had smoothed the ensemble using negative weights, and then it was just a straightforward ensemble. Where are these approaches coming from? One was Foldex, one was Pi Rosetta, which was the approach I kept mentioning. All of the other were just public notebooks. He had ensembled these and then used negative weights from some other models he had created. So the reason for smoothing part has been shared here. Combining ML models with positive block dropped his score. And his assumption was that it makes the values extreme. And even if he would have overfitted to the public LB, that would have caused dropping in the private LB. So to avoid shakeup, he assumed you needed some smoothing. You could simply try log transform, but the problem is we don't know which part of the prediction needs smoothing and which one doesn't. One method to solve this is to train a neural network, but as you have training data belonging to different distributions, that won't help. So he did something risky, which obviously paid off. He ensembled all ML models and subtracted them from an ensemble. And then he shared how he had done this. He hasn't pointed out the exact weights. Even Chris had asked how he did the smoothing. Uh, oh, he just answered this 3 hours ago. Sorry. So I was looking at this yesterday and he hadn't answered then, but now it's worth reading through. So let's read through this. So Chris asked him how he had applied the smoothing. Let's say you have three models A, B, C. First, you make a prediction like so. So you put weightage across the three models, and that gives you the ensemble. And then do you subtract pred minus A plus B plus C by 3? So basically, you have one set of weights that add up to plus one, and the second that add up to minus one. And he answers here, you're almost correct. The model used in either positive or negative will not be used again. So he points out how the addition and subtraction was done in this case. So when you ensemble, do you copy SciPy stats or rank data or normalize? Specifically, how do you pre-process ABC above? And his answer was he used SciPy rank data for both of them, and he believes that normalize or some other function could also be used in this case. I again missed this because I read this yesterday and he hadn't answered it then. But anyways, this was the second place solution. Again, for this competition, if you had been diligent like him and ensemble different approaches and did something risky that for his case paid off, you could have won the second place solution as well. And I'm sure it wasn't just pure luck. There was a lot of thinking involved as well. Because when you look at the LB, you can clearly see that he made 400 submissions. I'm sure there was significant effort there. All right, let's move on to the third place solution. I don't see anything in the chart, so I'm not sure why the chart is quiet today. Let me make sure the chart is coming through because sometimes I don't get messages. I hope people are still able to type messages in the chart. Okay, maybe it's just quiet because we all are just new to this. Sorry for that. Let's read the third place solution. Even the third place says they had not been able to build a reliable CV. So for the final result, it was just to pure luck. Unfortunately, he didn't save the notebook, and he doesn't remember the exact weights. But he shares the screenshots for his private and public scores, and as you can see, this is what got him to win the competition. So for training, he had used different data sets shared in the competition. We looked at PDB and what those were. Many of these were shared through the competition, and you could have used those to your advantage or diligently. For the first data set, he removed duplicate items and kept mutations with group greater than 20. I read through some of this, but again, it was too much domain knowledge for my brain at least, and I gave up after a while. But I assume it's relevant to how amino acids work and the like. And for the second data set, he had used this notebook or this discussion, as I understand. Okay, it points to a notebook. To use unstable mutations, he had trained two XGB models on two different datasets. For the feature engineering, he selected 21 amino acids closest to mutant amino acids. The relative distance were calculated. The average relative distance was calculated, and the angle was calculated. So, if you remember something painful known as trigonometry, and I pointed out earlier that enzymes or amino acids occur in 3D as these graphs we had seen. The way of calculating angles between them or these individual chain nodes would just be using trigonometry. Uh, I'm not sure if this approach is right or if arc cos is the correct one. I assume they use the correct approach, but I know for a fact that that's how you would do that. So that's another feature they had used. They'd used adjusted Blossom 62 to multiply SA and B factor. I again assume this is something very relevant to this competition, so I didn't try to dive into it. Features of the whole protein sequence, mutant amino acids, and 21 amino acids were extracted by ESM, and few other interesting features were added like so. So he had used this library that he applied to the entire data set and added these features like so. So far, some amino acid related features were used, some based on the 3D geometry of these enzymes, and all of the features used so far are very relevant to the domain. So they did, I assume, these guys did some domain study and used these models. And he had used an XGB model, and the top 220 features were selected, which got them this score. And then he used the second data set for another XGB model. He only used the features created in the first three steps, and which got him to this score. After which he did an ensemble. And then he was able to also find out the exact weights for the ensemble that were used. Here shared all of the particular models and the scores here, and you can read through this. So again, to summarize, the feature engineering was very relevant to the domain and very relevant to amino acids, and that's what this team had used. Um, Let me make sure if others have posted the solution or not. So I missed fourth and fifth, and let me just quickly search for that. See, this is exactly what I was ranting about, because I have to search for fifth solution, and then fifth solution, and then fifth position, and 5 POS. But nothing shows up, which means that these guys haven't published their solution yet. So we can move on to the sixth one. I'm trying to cover all the solutions that have been published. Some, as you can see, weren't. So we'll only cover the ones that were published, of course. I don't think the seventh place had either shared their solution as well. So I'll continue. Shujun is also a legend in the Kaggle community. He also honestly admits that he got very lucky because he started working when there were 4 weeks left, and his main idea was to use a rotation and translation equivariant network, E3NN. So this is an E3NN Euclidean neural network, and the library aims to create E3 equivariant neural networks. Um, Let me point this link in the chat, and you can read through this if you want. But again, this is relevant to the geometry and how I assume these behave in 3D space. Okay, let me hide that link now and continue. Which he says he failed to develop a strong solution. So the ensemble comes from public notebooks. But first he discusses the E3NN. So he had used the same dataset compiled by the Thermonet notebook, nothing fancy. This was a public notebook shared in the competition. Different approaches were shared. Thermonet was one of them. He says the good performance of Thermonet really surprised him because 3D conf is not rotation equivariant, which means that if you rotate a protein, it would give you different results. Obviously, you would think that this is a problem because rotating a protein structure shouldn't change its properties. But Thermonet outperformed his models. It could be that his E3NN is unoptimized and he didn't do it well, but he just writes praise for the model. Also, side note, he has also made his entire approach public. So you can check out the code as well on his GitHub repo if you want. Um, he simply ported the data pipeline, but instead of 3D voxel grids, a pixel in 3D is voxel. So voxel is just a 3D pixel. Um, he used the atom types and XYZ coordinates designed to tackle 3D structures with rotation, translation, and permutation. Some specifics of his network: he calculated the geometric center of the residue and mutated position, and only took atoms with a certain range, the range being 8. I assume this is the range between the nodes. And the input node feature other than atom types included residue and whether the structure is a mutant structure or WT structure. For ensemble, he used a eightfold E3NN with this particular notebook, and with zero point 0.8 and zero point 0.2. So he had given lesser weightage to the E3NN notebook. Now, he mentioned that he got lucky, as I understand, because he didn't select his here it is. He did not select his submission, and by just by chance, his best public LB ended up sixth. So if you don't select your submission, Kaggle by default selects the top two submissions based on the public leaderboard, which for his case got him to a sixth position. So this was the sixth position, and again, the secret was using the data prep similar to Thermonet, feeding that into an E3NN, and there he had used some specifics, ensembling this with public notebook. And since he assumed that E3NN wasn't the best performing, he gave the E3NN approach a smaller weight. So that's the sixth position solution. The seventh place has been shared. Again, I'll resume my rant here, but as you can see, I don't see anything here. I'll also refresh this leaderboard just to prove that point. But I was able to find it out after searching. And see, I had to specifically find another PNC of this place because the this particular team had used a dash in the write up. So anyways, that's part of my frustrations of making sure I don't miss out anyone, because I really want to cover all top solutions. um I'm just getting frustrated with this. Sorry about that. So here's the seventh place solution, and I read something which I really echo with. Chemistry was never of my interest, neither mine. But thanks to this competition, I was able to learn exciting topics I was unaware of, which I of course didn't get a chance. Um, the most important part of the solution is a single LGBM model, and they've shared some details of the hyperparameters used here. For dataset, this model was trained with the extra dataset, only DDG, which is a delta delta G. He then shares different features used. So information about amino acid and position for WTN mutation, database information returned by this particular library, and neighbor based information. For the ensemble, it was weighted like so, and the B factor was used from this particular notebook. That's it for the seventh place solution, a short write up. But again, this is another example where LGBM was really helpful, but this team or this individual had used many domain specific features, as I understand. Let's read the eighth place solution. Um, I'm sure they're not exaggerating, but this sentence was again something worth reading here. And I'm sure the team must have worked very hard even despite the conditions. So still they finished eighth, which is really awesome. Um, they shared different approaches here, so I don't think there's a summary at the top, but we'll lead through in order. At the beginning of the competition, they also noticed that Thermonet was giving a high contribution. So they studied a particular paper and decided to experiment with different neural network architectures, which ended up or which led them to Resonate 3D with a score. They iteratively worked on the architecture and found that this was the secret there. The same shape as Thermonet was used, and this model gave 0.477 on public LB, thus averaging a single parameter H bond underscore donor, hydrogen bond donor, yielded a fairly high result. To improve matrix, different variations of feature descriptors were used from this utility. And as we've seen earlier, many competitors just use open source libraries to create all different features or apply those to the data frame to basically add more columns with features. I assume this is something similar. This model is called AVGP3, which was a part of their final ensemble. They'd also use Rosetta, and they noticed that thermal stability is also well predicted by Rosetta. So they gave equal weightage to both the models, which boosted their score. And then they mentioned ranked Rosetta. The idea emerged to use weights for ensemble. Independent predictions of thermostability were created for each parameter separately for all mutations and then combined into an ensemble using the weights from energy tables. For the final ensemble, they read through the forums on the last day. I assume they must have had an adrenaline rush during the last day. Most Kagglers do the final ensembling exactly on the last second, so that's always cool to read. Um, they added one more notebook to their ensemble, and here are the weights that they ended up using. So again, hydrogen bond was relevant here. They ended up using something known as a resonate 3D and pruned that a lot to a shape similar to Thermonet. Used Rosetta and then combined those with a public notebook to finish eighth. Um, what's the energy table? SP is asking. Let's read through that. I assume it's um I'm trying to simplify and also remember, but energy refers to. So there were different things that came up in the competition. Delta delta G was the energy difference between folded and unfolded proteins. Um, I assume this shares energy calculations in different variations. I don't know the exact details. I should look into Rosetta to find that out, but I assume it's the energy calculation with different mutations or stuff like that being calculated. That's my understanding of it. I'm not sure if this is the exact correct answer. Yeah, reading through it, I don't exactly know what is what. Maybe someone else watching might know better. But that's my understanding of it. Um, oh, someone has answered already. It's Gibbs free energy. You want minimum energy to maximize stability. Thanks for answering that in a much much better way than I could have. Um, Energy for stability of protein structure. From Pavitra's answer, it sounds like that's the case. Thanks, Pavitra. And SP, I hope Pavitra answered your question. Um, here's the 11th place solution. And Tilly was legendary in this competition because he shared a lot throughout the competition. If you actually go to his profile, um, you'll see words that you might see in the competition. So I don't know any of these much about these things, but as you can see, he's really a domain expert, and his sharing throughout the competition helped many people. Um, SP says thanks, so I assume that answered this question. He says it takes a long time to figure out the domain knowledge needed for uh, protein language models and other things, yet many of you did it and made it easier for us to have a meaningful and productive competition. He says, and ensembling the solution is the way to go. Um, he started this competition on a lazy note. There were several very nice solutions based on test data, so he went along with that. Like everyone else, he was figuring out what molecular quantities can be calculated from test data and how to blend them. Along the way, there were many discussions that I found. He kept warning people of different factors not really predicting thermal stability. At some point, he decided to focus on getting best result or trying to make the best general model. So he ended up using Rosetta's energy function, which we just figured out what that does. But he never used the foldex before for the purpose of mutagenesis. It turns out foldex score alone got him to a really nice score, and Rosetta's lesser known programs got him some boost as well. In parallel, he started building a train data and doing a full scale AlphaFold 2 modeling on all wild type proteins. And he ended up with a large number of test mutants and train mutants, of which the last 300 models are yet to be completed. Then he calculated the DTM values for the train mutants, and he says it became difficult to do it in the second half, where he was manually verifying the protein residues for calculating the pH values. After doing all of this calculation, there was a tabular data set that could be modeled using any ML approach, and he chose light GBM and tabnet, which got him to some nice scores. He has also shared the importance of features by Sharp from light GBM. And he says you will see that energy based features were most important, followed by language embeddings expressed as PCA components. Then he shared how these models performed on the leaderboard and how he ended up ensembling them. Um, he said he didn't select any tabnet models, and the author of tabnet also had some interesting discussion in this solution write up. So I'll leave you to check that out. But if I were to summarize this, we can see that Tilly spent a lot of time coming up with this own data set, calculated a lot of stuff, came up with some features, and eventually a lot of features, constructing this tabular data set that you can use with a light GBM model or any tabular model. He also calculated different importance of all features. Light GBM gives an easy way of plotting these, and here's the plot of all of those. So as you can see, the Rosetta and Fold-X score was really important for his particular model. Sorry, the creator of Tabnet had hosted the discussion someplace else, so it wasn't here. Um, but in one of those top solutions, Tilly and Optimo as well, that's his name, had this discussion about the Tabnet models being relevant or not, and why many people chose to use it or not. So this was the 11th place solution. Um, Let me read the chart now. Only a sound knowledge in biochemistry domain can deliver a practical assumption. Kudos for analyzing all these notebooks. I'm not sure if that was for me. Um, I'm not sure what you're referring to, SP there. But here's the 13th place, and I know Darien. So Darien was also, I assume we were very active on Kaggle at the same point, so I know him through that, and I also know him through one interesting discussion. So I'll go on a tangent and we'll come back to this, but let me quickly find that. Um, back whale. Um, Let me search for whale. So I just want to point out a very cool discussion by Darian. So that's what I'm doing right now. There was this competition where you had to identify different whales, and yeah, I remember the title of the discussion as well. Darian ended up naming every single whale in that in that competition. He gave a name to every single example in that notebook, and I also told him a bit in that discussion. This was my favorite one. Uh, he said he was showing his partner that this whale is that whale, and actually ended up trolling him. Thankfully, he didn't take offense. So I was worried I might offend him, but that's how I know Darian. He's the guy who labels every single whale in a competition. Anyways, his team finished 13, so obviously I was excited to read this as well. Um, let's read through this, but the title says there's a full write up yet to come, so these are just the notes. I searched just before this live stream and I couldn't find a write up, so I'm going to use this. They say not even sure what worked and what didn't, but a few things that they did were, for half of the competition, they were in second place with public ensemble plus mutation deltas, except four big details were used. PA is a 2 to 1 by 2 to 1, and I don't know what that's referring to. I assume that's again something specific to a feature from somewhere. He says he took the mean of each row and treated exactly like PLDDT. It always scored much better than PLDDT for him. The second part was logit. PAE numbers were close to zero, but using PLDDT as an example was even more clear. With using 2413 predictions, the team found the predictions were fairly noisy. Instead of using a single run, they took the mean of hundreds, and with hundreds of views of normal for a position, it also gave them a standard deviation. And instead of taking the raw logit delta, by dividing the standard deviation, you get a z-score of how significantly it had deviated. They say they had tried Rosetta and Foldex. For that, they were mainly using the public notebooks, and they managed to get both Rosetta and Foldex running on Kaggle. They found that repair and relax were complementary and maybe competitive, but it appeared to get slightly more stable over repeats. Darian said he was failing, or he was failing to get anything that they were even remotely within the terms of getting the training data working. So they did some LB probing, and this got them some boost in the score. And finally, they say tab PFN was really helpful. So that's an overview of their solution. Just some random notes compiled, but I assume from what I can understand, the public notebooks were relevant for their write up, and eventually tab FEN and some other approaches had been used. Thermonet and some other things were relevant for their competition, and they also say how that micro ensembled everything along with Rosetta and Foldex. They've shared some more notes here, which I'm not going to read through. They are again very specific to the competition. Um, but that's a very quick overview of these notes. Again, I didn't understand it very well because these are just notes and not a proper documentation of the write up. I'm sure they'll come back and write this properly, so I'll keep an eye out for that. Um, but that's it for this live stream. I just wanted to cover the top solutions. I think we've covered all the this competition from them, not the whale one. Uh, I think we've covered all of the ones from the top goal teams. So that'll allow me to end this. Awesome. Thanks everyone for joining. This was slightly tricky because I'm foreign to chemistry, biology. I don't know what part of this is. I really don't understand where amino acids come. Is it biology? Is it chemistry? I don't know. Maybe it's an intersection. We'll keep meeting next week as well, and at least for this year, I plan to continue the study group. So consider subscribing if you aren't already. I'm already messing up. We'll meet again next week. I'll probably tweet about what competition I'll cover. It might be similar to one of the ones already going on. Um, I'm taking some NLP one relevant to the competition. I see David in the chat. Thanks for joining, David. All right, I'll see you next week. Thanks for joining, everyone.